sir.
Okay, that's great. Okay, so I hope you will able to solve the problem based on that.
Yes, sir.
Yes, sir.
Okay, that's good. Okay. I hope you are able to see this.
Yes, sir.
Yes, sir.
Okay, great. So in the last lecture, we have seen the successive differentiation. We have seen the Leibniz theorem, and then we have applied the Leibniz theorem for finding the nth derivative of the given product, as well as we have calculated n plus r derivatives. Again, now we'll move on, and then we'll go for the expansions of functions.
Sir, what is the name of the chapter?
This is expansions of functions we are going for. The same module, next topic we have Taylor and Maclaurin series. Okay, but actually that is expansions of functions. Okay, so we'll have now we need to understand how do we expand the function and where do we expand the function. Okay, so you are aware like binomial theorem. Okay, what we do in binomial theorem, a plus b bracket is to n, and then we expand this in the powers of a and b. Okay, so here we'll try to expand the function, okay, of x. And then let us see how we are able to expand it. Okay, so here there are two important theorems that we need to understand, or two important expansions that we need to understand. Okay, so the first is Maclaurin series expansion. First we have is Maclaurin series expansion. Okay, then we'll have the Taylor series expansion. So what is the relation between the Maclaurin series and Taylor series?
Oh.
Yes.
So I can't actually see. I can only see how now I can see.
You are able to see now?
So yeah, I thought that you were writing and then I couldn't see. So that's why.
No. Okay. So Maclaurin's series expansion. Okay. So we can have the abbreviation MAC, but MAC is used for many times. It is used for mean square error. Okay. So that's why we should not go for abbreviation which is not standard. Okay. So we go with Maclaurin series expansion. Okay. Now, this Maclaurin series expansion is about the origin. Okay, so we have a function. Okay, let f of x be the function, okay, of x. This is going to be the function of x. Then the Maclaurin series expansion of f of x about origin is given as so what is the Maclaurin series expansion? F of x equal to, this is in terms of powers of x. Okay, this is in terms of powers of x. So what we have here, f of x is equal to the value of f at origin 0 plus x times the value of first derivative of f at origin, then plus x square by 2 factorial and f double dash at origin plus x cube by 3 factorial and f triple dash at origin, and so on the terms. Okay, so this is what the formula we have for finding the Maclaurin series expansion of the function. Okay, so now we have to use this formula. So if you want to use this formula, what we have to do is we have to calculate the value of f at 0. We have to calculate its derivative and the value at 0. We have to calculate the second order derivative and value at 0. We have to calculate the third order derivative and the value of that derivative at 0. Okay, and so on. We have to calculate and then put it in the formula. So we are able to get the Maclaurin series expansion for any function. Now here the question is how many derivatives and how many terms we have to calculate. Okay, so be careful how many derivatives or how many terms we have to calculate. So if I want to claim that I have got the series, okay, then I must have at least 3 terms. Okay, so if I want to claim that I have got the series, then I must have at least 3 terms. So this is the first term, this is the second term, this is the third term. I have written the fourth here. Okay, but these terms should be non-zero. Okay, these terms should be non-zero. Okay, so that means if I want to find the expansion of any function, I must have 3 non-zero terms at least. I must have 3 non-zero terms at least. Okay, and hence, if we consider the terms f of 0, f dash of 0, f double dash of 0, f triple dash of 0. So if 3 terms are non-zero, then we can stop or we can write the expansion. If not, we have to go onwards and find 4 terms. Okay, so we'll go with the example so it will be more clear to you. Okay, so let's go for example. We'll be having find the Maclaurin series expansion. Okay, find Maclaurin's series expansion of f of x is equal to e raised to x. Okay, so simple function we have. We'll try to find what is the expansion of e raised to x, or what is the series expansion for this function e raised to x. Okay, so let us try to find the expansion for this function. So we go with the solution. Okay, what we'll be having, let f of x is equal to e raised to x. See, what we want to find, we have to find what is the value of f at 0. So I can write f at 0. Okay, so the value of the function at origin. What will be the value of the function at origin? If I put x is equal to 0, what I'll get?
1.
1. Yes.
1.
So easy, correct? Then we go for the next term, derivative. So f dash of x. This is being an exponential function, we'll get e raised to x. And hence, we have to find the value of this derivative at x is equal to 0 again. That is again 1. So we can go for next derivative of this function and we get it as e raised to x. Again, we have to calculate the value of the function at 0, the value of this double derivative at 0. It's going to be 1. And so we go to the next term. So you'll be having the third derivative. Okay. So f triple dash at x. This is being exponential function. It remains as it is, and hence we are able to get the value of this third derivative at origin, and that is going to be 1. Okay. So we can have. Now think of the terms here. What we require f at 0, f dash at 0, f double dash at 0, f triple dash at 0, and then you can see this value is going to be 1, this value is going to be 1, this is also 1, this is also 1. So we got 4 non-zero terms. We got 4 non-zero terms. At least 3 are required, and hence we can say we can write the Maclaurin series expansion. So we write here by Maclaurin's series expansion. We have, okay, so we have to write the formula once again, and hence I'll write the formula. So we'll be having f at x is equal to, okay, so what we have here, f at 0 plus x f dash at 0 plus x square by 2 factorial f double dash at 0 plus x cube by 3 factorial f triple dash at 0 and so on. Okay, so that's what we have. Now put up these values. So we can have this f of x is equal to 1 plus x into 1 plus x square by 2 factorial into 1 plus x cube by 3 factorial into 1 and so on. See, this plus dot dot dots are very important. Okay, because the derivative of this function exists, but we have not calculated. Okay, so that means there are terms which exist, but we have not written here. Okay, and hence we can write e raised to x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial and so on. So this way we are able to get the expansion, okay, for this function f of x is equal to e raised to x. So we got here the Maclaurin series expansion of the function f of x is equal to e raised to x. So do you have any doubt in this question?
Sir, using Maclaurin's series expansion, we can find expansion of any function, sin x, tan x, cos x.
Yeah, if the function is, there is a condition, if the function is having the expansion, that means if it is infinitely differentiable, definitely we are able to get the expansion of that function. Okay,
Yes.
yes. So we'll try to find for another example.
Sir, I had a doubt.
Yes,
Sir, but what if the function is finitely differentiable?
yes, correct. Okay, so if the function is finitely differentiable, still we are able to find the expansion, but that is the next part we need to go for. We'll go for that also.
Okay, sir.
Yes. Any other doubt?
No, sir.
Okay. So yes, we can write this in terms of summation also. Okay. So if you want to write this in terms of summation, what you can have is, or other way we can write e raised to x is equal to summation n running from 0 to infinity. Okay, we have x raised to n upon n factorial. Okay, so you can see, put the value of n and you can get this expression. Okay, so this is the other way to write the same series. This is the Maclaurin series expansion only. Okay, so now let us try the another example. Okay, now if it is e raised to minus x, easily you are able to get into e raised to minus x, because as we did for e raised to x, we can do it for e raised to minus x and then get the expansion of e raised to minus x. So let us try the another example. Okay, find Maclaurin series expansion of f of x is equal to cos x. Okay. When we say Maclaurin series expansion, obviously it is about the origin. So if we write about the origin, that's okay. If we do not write about the origin, that's also okay. So we go with the solution. Okay. Now what we have, like f of x is equal to, what is the term we'll be having? Cos x. And hence our first task is to find what is the value of the function at 0. So what will be the value of the function at 0?
1, sir.
1. Obviously, cos of 0 is going to be 1. Now let us try the first derivative. So what will be the derivative of this cos x?
Minus sin x.
Correct. So it is minus sin x. And now tell me what is the value of this derivative at 0?
0.
0. Okay, so we have calculated two terms, but this being a 0 term, we cannot count it. Okay, this is a 0 term, so we cannot count it. That's why that's what we need to understand. Okay, so here this term will not be counted because it is 0. Okay, now we go for the next derivative. So f double dash of x. So what is
Minus
going to
cos
be?
x.
Minus cos x, right? And hence, what will be having? F double dash
Minus
of
1.
0 is equal to minus 1. So,
Minus 1.
yes. So f triple dash at x is equal to
Sin x.
yes. So we get sin x.
0.
Hence, f triple dash at 0 is equal to 0. So again, this term is going to be 0. So that's why again this will not be counted. Okay, we cannot count this term because we want non-zero terms. So what we are able to count, we are able to count what is going to be f at 0. Then we can count what happens to f double dash at 0. But are these two terms sufficient? No. Okay, so only two terms cannot claim the series, and that's why we have to go for. So what we can go for? We go for the fourth derivative. So what will be the derivative? We can have this going to be cos x.
Cos
And
x.
hence, your fourth
1.
at 0 is equal to 1. We go for fifth derivative of x, f of x. So it will be again minus sin x. And hence we can have your fifth derivative at 0.
And now it will repeat.
0. Yes. Okay. But we want 4 non-zero terms. Okay. We want non-zero terms. No. So we got one non-zero term. We got the second one. We got the third one. Okay. So what we have to do is, three are at least 3 are required. Okay. So if you can count or you can calculate the next also. Okay. So what we have here, if I consider the next derivative, what will be the next derivative? Sixth derivative.
Minus cos x.
Yes. So sixth derivative at x. So it will be minus cos x. And hence you can have the sixth derivative at 0. And that's going to be minus.
-1.
Okay. So the values are easy to calculate, but we need to understand how many values we have to calculate. Okay. And that's what we got here, that This four values, this is non-zero, this is non-zero, this is non-zero, and this is non-zero. And hence we can write the Maclaurin series. Okay, so what we can write here? Maclaurin series. So we can write here y Maclaurin's series. We have. So what we'll be having here, f of x is equal to, always write a formula so that there are less chances you will go wrong. Okay, so x f dash at 0, x square by 2 factorial f double dash at 0, plus x cube by 3 factorial and f triple dash at 0. Okay, so this is what the formula is. Now you can see what are the terms that we have calculated. So we have f is non-zero, f double dash is non-zero, f fourth is non-zero, f six is non-zero. So here what we have to write is, we can write f of x is equal to, this term is going to be 1 plus x into 0 plus x square by 2 factorial into minus 1 plus x cube by 3 factorial into 0 plus x raised to 4 by 4 factorial into 1 plus x raised to 5 by 5 factorial into 0 plus x raised to 6 by 6 factorial into minus 1 and so on. So you can see these terms f dash at 0, f triple dash at 0 and f5, these are going to be 0, whereas the even terms, all the odd terms are going to be 0 and even derivatives are going to be alternative plus minus. So this first was plus, then the second was minus, then fourth was plus, and the sixth is minus. Now simplify this. So what we have, this is cos x. So you can see this is going to be 0. So 1 minus x square by 2 factorial plus x raised to 4 by 4 factorial minus x raised to 6 by 6 factorial. So here you can see the cosine function can be expressed in terms of powers of x. So it can be expressed in terms of powers of x. And if you want to write this in terms of the summation notation, so yes, obviously we can write this. Okay, or now this is cos x equal to, so what we'll be having, n running from 0 to infinity. So x raised to 2n. And here we need to understand n running from 0 to infinity. And here we'll be having minus 1 n s2 n. Let's say minus 1 s2 n. Our first term is going to be 0. 1 is going to be 2, is going to be 3. So minus 1 is 2 n. And here we have x raised to 2n on, or here n factorial. Okay, so if you put x is equal to 0, you will get first term. X is equal to 1, you will get second term. N is equal to 1, you will get second term. N is equal to 2, you will get the third term, and so on. So we can write this in terms of expansion also, and in terms of series summation notation also. So these both are the same series. Only the change is that notation. We have summation notation. Okay. So is there any doubt this example? Is there any doubt in this example?
No, sir.
No, sir.
No, sir.
Okay. So here you can see some derivatives are zero, some derivatives are non-zero. And we have calculated or we have counted only the non-zero derivatives. Okay, so we always look for the non-zero terms. If they are going to be zero, then they will be just vanishing. Okay, so we have to consider non-zero. Now let us go for the another example. Okay, so go for another example. And we can write find the Maclaurin series expansion. Log of 1 plus x. Okay, so here we need to find the derivative of this function, and then using that derivatives, we have to find the Maclaurin series expansion. Okay, so let us see how we are able to find the derivatives and the Maclaurin series expansion. Okay, so what we have, let f of x is equal to log of 1 plus x. So what will get f at 0?
0.
Yes, it is going to be 0. Now find the first order derivative. So it is 1 upon 1 plus x. What will be the value of this function at 0?
1.
1.
1. It is going to be 1. What will happen to f double dash at x?
Minus 1.
Minus 1
Minus
by
1.
Minus 1.
1 plus.
So it is minus 1 upon 1 plus x bracket square. Is that okay?
Yes, sir.
Are you
Yes.
getting this? Yes.
Yes,
Okay.
sir.
And hence, what will be the value of f dash, f double dash at 0?
Minus 1.
Minus 1.
Minus
It will be minus 1. See, this term is going to be 0, so we cannot count this term. And hence, we have to go to the next derivative. So,
Sir, up to how many terms we have to find? 4 terms?
yes, non-zero, 4 non-zero.
Yes.
Okay, because this is 0 term, we cannot count it. This is the non-zero term, we can count it. This is the non-zero term, we can count it. Okay, then you will be having f triple dash at x. So can I have, this is 2 upon 1 plus x bracket square. Here it will become minus 1. So again it will become bracket cube. So is that okay?
Yes, sir.
Yes, sir.
Okay, because again this minus 2 if we'll write, then it will become minus 3 and minus 2 will come down. So minus 2 into minus 1 is going to be 2, and hence you will have this term. So now what we'll have at 0?
2.
2, sir.
Is it going to be 2? Now let us calculate the next derivative. Okay, so here if I consider the next derivative, is it that minus 6 upon 1 plus x bracket raised to 4, and hence
Yes, sir.
you will be having the fourth derivative at 0. It's going to be minus 6. Are you getting this?
Yes, sir.
Okay. So now we got, are we ready to write the expansion?
Yes,
No,
sir.
sir. The first term was 0, right?
Okay.
Yes.
This is the second term. This is the third term. And this is the fourth term. Okay. So do you have any doubt now? Is there any doubt?
No,
No.
sir.
No, sir.
No, sir.
No, sir.
We can write by Maclaurin's series expansion. Big 8. Okay, so what we are able to get is, you can write here f of x is equal to. Okay, so we have f at 0 plus x, f dash at 0 plus x square by 2 factorial, f double dash at 0 plus x cube by 3 factorial and f triple dash at 0. And so on. You're getting this formula?
Yes, sir.
So once we have this formula, let us write down the terms. So we have f of x is equal to f at 0. So we have already calculated the value of this function. So you can see what is f at 0?
Yes, it's 0.
It's going to be 0. Okay, so if f at 0 is going to be 0, then what we get here? So this is 0. Then plus x into minus 1. Okay, so you can see f dash at 0. So this is going to be 1. X into 1 plus x square by 2 factorial. This is the value of f double dash at 2. So it is going to be minus 1
Minus 1.
plus x cube by 3 factorial. This one is going to be 0. At x cube, what do you have? Sorry, x cube you are having 2. Okay, so this is going to be 2. And plus x raised to 4 by 4 factorial. And this is going to be minus 6. Is that okay? So here,
Yes, sir.
whatever the expression we have, we are putting these values now. We have put the value of f at 0. We have put the value of f dash at 0. We have put the value of f double dash at 0. And we have put the value of f triple dash of 0. And we have put the value of f at fourth derivative of f at x is equal to 0. Now simplify. So what we can have is f of x is equal to, this is going to be x minus x square by 2. Okay, so you can see this 2 factorial is going to be 2 itself, and hence you will have minus 1. So this is minus here, so it is going to be minus x square by 2. Now, you can think of this term. So what this term is going to be? Is it
X cube by
x cube by 3?
2x cube by 3 factor.
minus
It is
x
3
square.
factorial. No, it is 3 factorial, so 2 will get cancelled. So it will remain
Yes.
3 only.
Minus
Next,
Minus x raised to 4 by 4.
a raised to power 4.
so this will become x raised to 4 by 4. And plus there are terms. Right. So plus there are terms which we have not calculated. Okay, and that's going to be the Euler series expansion of the function. This is what we have, and this is what we are going to do. Okay, so we have any doubt? These 2 examples.
No, sir.
No, sir.
Right, you are able to get this formula. Now, similarly, we can find for log of 1 minus x. Okay, we can find for sine x. Okay. Then we can find for the remaining functions. Okay. So if we have a given function, then what we do is we try to find the value of the function and its derivative at origin. Okay, this is the basic idea of the Maclaurin's expansion. Okay, or Maclaurin's series expansion. Okay, now we try some more example. Okay, so let us see some other example. Okay, so let's go with the example. Fine. Maclaurin series for f of x is equal to. And now, yeah, now for this function. Something over minus x. Okay, so see 1/1 minus x. So let us try to find, so logarithm will become the previous one. So we go with the solution. What we have laid f of x is equal to, what is f of x? 1/1 minus x. What is our first step? Our first step is find the value of the function at 0. So what will be the value of this function at 0?
1.
So is it going to be 1? Is it going to be 1?
Yes, sir.
Yeah.
Yes, sir.
Yes, sir.
Now find what is f dash of x. You are able to get, is that 1/1 minus x square?
Yes. 1 minus x whole square.
Whole bracket square.
Whole square.
Whole bracket square, right?
Hmm.
Okay, so we get 1/1 minus x square. What happens to the value of the derivative at 0?
1.
1.
Yes. So what is the next we have? F double dash of x. Okay. So this is equal to, what will be the derivative of this term?
2/1 minus x cube whole cube.
This 1/1 minus x bracket cube, right?
2/1.
Sir, shouldn't that be -1 in f dash x?
Yes, sir.
Yes,
Minus
sir.
1/1 minus x whole square.
No chain rule will be applicable.
Derivative of 1 minus x also we are taking.
Yeah.
So are you getting this 2/1 minus x bracket cube? Or we simplify, okay? So what I have f dash of x. Okay, so see what we have. We have f dash of x as 1 minus x bracket raised to -2. Is that okay? Can we write it like this? Now differentiate. So we'll be having f double dash of x. So this will be -2, 1 minus x raised to -3, and the derivative will be -1. So it is 2 into 1 minus x bracket cube. And hence we can write here. So this is f double dash at x equal to. Okay, so you got here 2/1 1 minus x bracket. Are you getting this term?
Yes, sir.
Okay.
Yes, sir.
Because if you can get this, then the remaining terms will be very easy.
Sir,
Okay.
that f double dash x is
Yes.
equals 2 into 1 minus x raised to power minus 3, na?
Yes. So it is going to be minus. Yes. So here I have written it 2 upon 1 minus x bracket 2. So we got f double dash at x is equal to 2 upon 1 minus x bracket 2. And hence, what will happen to f double dash at 0? What will be the value of if I put this x is equal to 0, I'll be having 1 cube. So 1 cube is 1. So this is going to be okay. So we got f double dash at 0 is going to be okay. Now we have what you're having f double dash of x is equal to 2 upon what is the term you'll be having here? 1 minus x bracket cube. So we differentiate this again. See how many derivatives we have got. We got f at 0. We got f dash at 0. We got f double dash at 0. Now we'll calculate f triple dash at 0. So if we calculate f triple dash at x, okay, we'll calculate for 0 later. So is that 6 upon 1 minus x raised to 4?
Yes, sir.
Because what will happen? This cube will go in the numerator. Okay, again you will be having minus 1 upon 1 minus x. Okay, bracket raised to 4, and this minus 3 will become plus 3. Okay, so this way we are able to get the derivative, the third derivative as x 6 upon 1 minus x bracket raised to 4. Now calculate the value of this third order derivative at 0. So if you put x is equal to 0, what is the value?
6.
6. Okay. So you can see we got the value. Okay. We got this value f at 0. We got this value f dash at 0. We got this value f double dash at 0. And we got f triple dash at 0. So is it possible that we can write Maclaurin series? Is it possible?
Yes, sir. We can write.
Yes,
Sir,
sir.
it is possible now.
Yes, we got the 4 non-zero terms. At least 3 are required. I am trying one more. Okay, so at least 3 is required. Okay, and hence we can write here by Maclaurin's series exponent. We get. So what we are able to get is f of x equal to, so f at 0 plus x f dash at 0 plus x square by 2 factorial f double dash at 0 plus x cube by 3 factorial f triple dash at 0 and so on. Now put up these values one by one. So we can have f of x is equal to, we can see this is going to be 1. Okay, so we have this is going to be 1 plus x into 1 plus x square by 2 factorial into 2 plus x cube by 3 factorial into 6. And now, we have this is 1 upon minus x is equal to. So this we got 1. This is x. This one. We can have x square by 2 factorial. What is the value of 2 factorial?
2.
So this 2 and this 2 factorial will get cancelled. Is that okay?
Yes, sir.
Yes,
Yeah. Yes, sir.
Okay. So what remains is x
X
square
square.
plus. Now what is the value of 3 factorial?
6.
6. It will get cancelled.
6 will get cancelled
Yeah.
and we'll be having
X cube.
plus 1. Okay. So that's what we have. So we got the term 1 upon 1 minus x is equal to 1 plus x square plus x cube. So this is going to be the correct series for the function that 1 upon minus x. So is there any doubt in this example?
No, sir.
No, sir.
All of you are able to get this?
Yes, sir.
So that's good. You got this expansion. Okay. Now we need to understand what is the expansion using this standard ones. So these are sometimes called as standard series expansion. Okay, or we have seen. Yeah. So this is 1 plus x square plus x cube, right? Okay. So we have seen this expansions. Now, similarly, if we have 1 upon 1 plus 1 upon 1 minus x, we are able to calculate 1 upon 1 plus x also.
Sir, I have one doubt.
Yes,
Sir, now we are stopping until 4 terms, right, sir?
yes,
So we can stop until 3 terms also, sir?
yes, we can.
Okay.
So that's what initially I said. I can claim that I have a series if I have at least 3 terms. Okay, then only we can claim the series. In 2 terms, we cannot claim the series. So to say that this is the series expansion, I should have at least 3 terms. First 3 terms. Okay, but I'm calculating one more than required. So you can stop at 3 terms also. Okay, but as we have seen in one example, that sometimes 3 terms are not sufficient. Okay, sometimes 3 terms are not sufficient. And if they are not sufficient, then we need to take care that we will get the next non-zero terms. Okay, and that's how you are able to get the series for the function. Okay, so got this one? Any other doubt?
No, sir.
Okay, so if you can find the expansion for this, let us try to find the Maclaurin series. Expansion of Rx. Okay, so let us try to find the Maclaurin series expansion. Okay, so here just I'm going to change the notation from f to y. So what I'll be having, let y is equal to Rx. Okay, So suppose y is going to be tan x. Then what will be the value of y at 0?
0.
Tan 0 is going to be
0.
0.
0.
So this value is going to be 0. Okay. Now, what will be y dash?
Sec square x.
X square x.
Is going to be sec square x. Right? So can we write this as 1 plus tan square x?
Yes.
Is that okay?
Yes, sir.
Yes.
Yes. So what is 1 plus this tan square is going to be y square? Is that okay?
Yes, sir. Yes, sir.
Because y is equal to tan x, no? We got y dash is equal to 1 plus y square. And now we are interested in value of y dash at 0. So what is the value of y dash at 0?
1.
1.
1.
Big 1. Okay, now differentiate this. Y double dash is equal to. What is the derivative of this 1? Will be 0.
0.
What about this y
2
square?
y dash.
Yes. So it is going to be 2y y1. Okay. And hence, what is the term we'll be having here? So y double dash at 0 is equal to what you can have?
0.
Y is equal to 0. So if this y goes 0, that means this product goes 0. Okay. Now think of the next. So we have y double dash is equal to 2y y1 or y dash. Okay. Write this y1 as y dash. Okay. And now we want the next derivative. So y triple dash is equal to this 2 remains as it is. Is that okay if I write y1 dash square?
Yes, sir.
This 2 is common. Okay, this 2 is going to be common. Then we have y and y dash. So the derivative of first u into v rule we have to apply. So the derivative of this first y is going to be y dash. And already I have y dash. So I'll be having y dash into y dash. That's we can write always as a y dash square. Now plus. Okay, so this y remains
Y
as
double
it is, and this will be y double dash. Yes, right. Okay, and hence, what will be having y triple dash at 0? Okay, so this is going to be 2, this is going to be 1, and this is going to be 0, so it is 2. So we can write y triple dash at 0 is equal to. Okay, so you can see here we got y dash at 0, then we got y triple dash at 0 is the non-zero term. Okay, so we need to have at least one more non-zero term to claim the series. Okay, so what we can do is we can again differentiate this term. Okay, so let us differentiate this term. So we'll have the fourth derivative. What is the term here? We'll be having 2y dash square. What will be the derivative of this 2y dash square? Is that 2y dash y double dash?
Yes.
The derivative of this term. When this 2 will come down, then y dash and y double dash. Plus See this term, u into v rule. So y dash, y double dash plus y, y triple dash. Is that okay? Are you getting this?
Yes, sir.
Yes, sir.
Now see what we get here 2 times. This is 2 times y dash, y double dash. This is y dash, y double dash. So can we write 3 times y dash, y double dash plus y, y triple dash? Can we write it like this? So this term and this term we have combined. Okay. Now think of what is the value of this y 0 at 0.
0.
So y is going to be 0, y double dash is going to be 0. So that means this is going to be 0. Okay. So we got this y fourth derivative of y at 0 equal to 0. Okay. So we got the first derivative exists. Second derivative is 0. The third derivative we have seen. The third derivative is going to be 2. And we got now the fourth derivative. Okay. So here we can see that the fourth derivative is going to be again 0. So if fourth derivative is 0, how many terms we have obtained yet? This is the non-zero term. This is the non-zero term. So we got only 2 non-zero terms. And in the case that it is being lengthy, so here you can see the next derivative. Okay, so what is the next derivative? We have y5. So we have to find the fifth order derivative. Now, if we find the fifth order derivative, then we have here, this is y5 is equal to, see, this 2 remains as it is. Okay, now here again you have to use u into v root. Okay, so this 3 remains as it is. Then we have y double dash square plus y dash y triple dash. Is that okay? Are you getting this u into v root? First I differentiated this term. So we got y double dash and y double dash. So y double dash square. Then we have kept this y dash as it is. And we differentiated this y double dash, the derivative of y double dash will be y triple dash. Plus. So again you have u into v root. So it is y dash y triple dash plus y and fourth derivative of this term. Okay, is that okay? Are you getting this?
Yes, sir.
Okay, simply and slowly you will go, then you will not have any problem, but definitely you will get the terms. So simplify this. So fifth derivative is equal to 2 into, this is 3y double dash square plus 3y dash y triple dash plus y dash y triple dash plus y and y4. So y5 is equal to 2 into 3 y double dash square plus this will be 3 plus 1. So it is 4 y dash y triple dash and plus y y4. Now the fifth derivative at 0 equal to. So we know y double dash is going to be 0. This y double dash is 0. So we can have, this is going to be 2. This is 0 plus 4 times
2.
y1. So y1 is 1. and y3 is going to be 2. So it is going to be 1 and this is 2 plus y is 0. So we can write
16.
the fifth derivative at 0
16.
is equal to. So how much is going to be?
16.
16.
Yes. So we got this derivative at 0 equal to 16. Now you see what is the pattern you can observe. See, y at 0 is 0, y1 is non-zero, y2 is 0, y3 is non-zero, y4 is 0, and y5 is 0. Okay, so that means if I want to calculate the next term, y6 is going to be 0. 7 will exist. Okay, what will happen? Y6 will be 0, but y7 will exist. Okay, so now we have to think. So as I said, in this case, at least 3 non-zero terms are required. So do we have the 3 non-zero terms?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so can we write the Maclaurin series?
Yes. Yes, sir.
Because we have 3 non-zero terms definitely, so we can write the Maclaurin series for the given function. And hence, we can write here by Maclaurin's series expansion. We have. Okay, so what you're having, y at x is equal to y at 0, x, y dash at 0, x square by 2 factorial, y double dash at 0. Okay, so instead of f now I am using the notation y. So what we have here, y of x is equal to. In this case, what you can see, what is the value of y0 is going to be 0. y1 is
0.
1. y1, y dash is going to be 1, no? Y dash is going to be 1. Y double dash is 0. Y triple dash is 2. Okay. So we write here, this is going to be 0 plus x into 1 plus x square by 2 factorial. This is 0 plus x cubed by 3 factorial. And this is going to be, this only we have here, to be 2. Okay. So this is 2 here. And plus x to 4 by 4 factorial into 0 plus x raised to 5 by 5 factorial. This is 6. Okay, so that's what we got. Now simplify this. Okay, so it is going to be x plus this is 2x cubed by 3 factorial. So we have this plus sum is going to be 0. So 16x raised to 5 from 5 factorial. And plus there are many more. So it is going to be x plus x cubed by 3 plus. Okay, so think of this term 16 by 5 factorial.
2x raised to power 5 by 15.
So it is going to be 2x raised to 5 by
15.
15. Okay, and so on. So what we calculated, actually, we calculated tan x. So tan x is x plus x cubed by 3 plus 2x raised to 5 by x is going to be and so that's what we got. That's what we can say. What the Maclaurin series expansion. For
Sir, we
this
cannot write it in sigma. Na?
pattern,
Can we write it in sigma operator?
yes, we can write in terms of sigma operator. Okay, but you need to write this 2 and 15, 1 and 3 that you have to relate. Okay. So if you are able to relate that, then definitely we are able to write this. So that's what we have. So do you have any doubt this example?
Sir,
Yes.
can you give 5 minutes break, sir? Can you give 5 minutes break?
One break. Okay. So no problem. We'll have a break for 5 minutes. Okay. Then again we'll continue. Right.
Okay, sir.
Okay. So now we are able to expand the given function in terms of powers of x. Okay. And that is what we have the Maclaurin series expansion. Now, as somebody has asked me the question in the previous session that what if it is a finite degree? Okay. Well, that's good. Then we have the answer that Taylor series. Okay. So we need to consider the Taylor series. Now, what is the difference between the Taylor series and Maclaurin series? Okay. So we have here Maclaurin series. We have solved for the Maclaurin series. So I hope you will able to solve more problem based on this. What we have to do in Maclaurin series, we just have to find the derivatives and find the value of the derivatives at 0, x is equal to 0. So, and then use the formula for Maclaurin series and we are done. So now we need to understand the next. So what we have Taylor series. Next one. So this Maclaurin series expansion is about the origin, but Taylor series expansion is about any arbitrary point. Okay, so we have the Taylor series expansion let f of x be the function of x, then the Taylor series expansion of f of x of x is equal to a is given as. So what we have f of x is equal to f at a plus x minus a f dash at a plus x minus a bracket square by 2 factorial f double dash at a plus x minus a bracket cube by 3 factorial and f triple dash at a plus 1. So now you can see the difference between the Taylor series and Maclaurin series. So this is the Taylor series. Okay. And then we have this is the formula for Maclaurin series. Okay. So we have seen the formula for Maclaurin series. Now you can try to identify the difference. Here, this is the formula. F of x is equal to f at 0 plus x times f dash at 0 plus x square by 2 factorial f double dash at 0 plus x cube by 3 factorial f triple dash at 0 and plus on the terms. And now you can see this Maclaurin's Taylor series formula. So f of x is equal to f at a plus x minus a f dash at a plus x minus a bracket square by 2 factorial f double dash at a and plus x minus a by 3 factorial x minus a bracket cube by 3 factorial f triple dash at a. So you can see the Taylor series and you can see the Maclaurin series. So you have both the Taylor series as well as the Maclaurin series. So what you can guess or what relation you can see in Taylor series and Maclaurin series?
X is replaced by x minus a.
X is replaced by x minus a. Good.
And f of 0 is replaced by f of a.
F of 0 is replaced by f of a.
A is replaced by 0.
Yes.
So can we say that if A is equal to 0, then we get Maclaurin series?
Very good. So if A is equal to 0, then we get Maclaurin series. So what you can say? Which is a general case and which is a special case?
Taylor is a general case.
Taylor is a
General
special
and Maclaurin is
Taylor is
special.
One by one. If you raise your hand, then I can ask you to say. Okay. So, yes, Mansi.
Sir, Taylor series is general case and Maclaurin series is a special case.
Okay. What Dhruv Mandlik?
Sir, the Taylor series is a general case and the Maclaurin series is a special case.
Okay. Subhada?
Yes, sir. Taylor series is a general case and Maclaurin series is special case.
So all of you got this relation between the Taylor series and Maclaurin series?
Yes, sir, we got it.
Yes.
Okay. So see, Taylor series is about any arbitrary point. Okay. That's what I wanted to show you. So if we consider this is a real line. Okay. So here x we have anywhere on this real line. And now I am considering a point A. Okay. So I am trying the difference between x and A. Okay. So this is the difference between x and A. So that means x can be nearby this term A. Okay. And we are finding the difference. And then we are getting the series about this arbitrary point. This is a general point. It can be any point. So A. But when we think of the Maclaurin series, we shift this A to 0. Okay, we shift this A to 0. And hence, here we'll get Maclaurin's series. Here we have Taylor series. Okay, so it is obvious that if I consider a special case, okay, that is A is equal to 0, then we get Maclaurin series. And this is nothing but the general case. Okay, so A can be anything. Okay, so A can be 1, A can be 2, A can be anything. Okay, but when I set this A is equal to 0, then I will have only one choice, the origin, and hence it is going to be the Maclaurin series. Okay, so sometimes it is said that the Taylor series, but written as the Maclaurin series, because Maclaurin series is the Taylor series about x is equal to 0. Okay, Maclaurin series is the Taylor series about x is equal to 0. So here I have taken x is equal to a. Okay, so it is a general case. If I put x is equal to 0, then it is going to be the S origin. Okay, that's what we have. So we have any doubt now in this relation of Taylor and Maclaurin? Do you have any doubt for the relation between the Taylor series and Maclaurin series?
No,
sir.
no, sir.
Okay. That idea is clear to you now?
Yes, sir.
Yes, sir.
Sir.
Okay, so we can get the expansion, okay, in terms of x minus a, or we can get the expansion in terms of powers of x. Now here, there are several ways to write the same formula. Okay, so you can see, I'll be writing this in a different way. Okay, so what I can have, put x minus a is equal to h. So what we'll get, x is equal to a plus h. Is that okay?
Yes, sir.
If I put this x minus a, I don't want to see in terms of x minus a, but I'll write this term as h. Okay, so if I write this term as h, then I'll be having x minus a is equal to h. So x is going to be a plus h. And hence, the same formula, above formula can be written as a plus h. Okay, so this is a plus h is equal to. So you have here f of a plus h times f dash of a plus h square by 2 factorial and f double dash at a plus h cube by 3 factorial and f triple dash at a, and so on. Okay, so you should not be surprised that this formula or this formula, they are different. Okay, but actually they are same. Okay, so this is the formula when we replace x minus a by h. So you can see that formula like this. Okay. Now here I replace this a by x. Okay, so we have f of x plus h. So suppose this a is replaced by x. Okay, then what this formula will be? This formula will be f of x plus h times f dash at x plus h square by 2 factorial f double dash at x plus h cube by 3 factorial and f triple dash at x and so on. Okay. Now the question is, if I have one formula, then why we have derived the remaining two, or why we required this remaining two? So the answer is, as per the need, we have to write the formula. Okay, so the first formula is in terms of x minus a. So if the question is, find the expansion of the function about x is equal to a, then we have to use first formula. Okay, the second formula is used for approximation. Okay, so we do not find only the expansion, but we also approximate the value of the function using Taylor series. Okay, so this Taylor series is also useful in finding the approximate value of the function. That's why the second formula. If I want the expansion in terms of powers of h, okay, then we have the third formula. So that's how, depending on the requirement or depending on the problem, we can find the formula or we can use the formula. Okay, so either you use first one, or you use second one, or you use third one. Okay, so that's why these are the different variations, and we have seen how simply we are able to obtain this variation. So is there any doubt in this formula? Is there any doubt in these formulas?
Excuse me, sir.
Yes.
Sir, can you please repeat when to use which formula?
Yes, sure. Okay. So see, if you have a question that you need to find the expansion in terms of x minus a. Okay. So if the question is finding the expansion of the given function about any fixed point or about any arbitrary point other than 0, because if it is 0, it will go to Maclaurin series. Okay, so other than 0, then we have to use first formula. Okay, if we want to find the approximate value of some function, okay, then when the problem will come, you will better understand this also. Okay, then we have to use the second formula. And if we want to find the expansion in terms of powers of h, okay, then we use the third formula. Okay, so function of x expanded in terms of powers of h. Okay, then we use the third formula. Is that clear?
Yes, sir. Thank you, sir.
Okay, welcome. Okay, so now let us try to go for the example. Okay, so is there any other doubt, or you are able to understand these formulas now?
Yes, sir.
Okay, so let us try an example. So we go with the example, and here the question is now: find the expansion of f of x is equal to x cube minus 2x square plus x minus 1 about x is equal to see the question, read it once again. Okay, so what we have here, we have to find the expansion of this function about x is equal to, okay, or I can frame this question in other words as expand f of x is equal to x cube minus 2x square plus x minus 1 in terms of x minus 2. Okay, the same question I have framed in two different ways. One is find the expansion of this function about x is equal to 2, and the other is expand f of x, the same function, in terms of x minus 2. Okay, so I want you to choose the formula, whether we have to go with the formula 1, formula 2, or formula 3.
Formula 1, sir.
Yes, correct.
Yes,
Okay,
sir.
so that's true. This is how you need to understand a question. Okay, and once you understand the question, immediately you can relate to the formula where I can see this term, and then yes, done. Okay, so now you got the idea that first formula to be used. Okay, so if you want to use the first formula, what is the value of the a? So let f of x is equal to x cube minus 2x square plus x minus 1. Okay, so what is the value of a here?
2.
2, sir.
Okay, so we can write here a is equal to, okay, and hence what we have to do is we have to find the value of the function at 2. Okay, so what we have to do is we have to find the value of the function at 2. Right? Okay. So tell me what is the value, calculate this value. So what will be having 2 cube? Okay,
One.
right here.
1.
Sir, 1.
So you are getting 1, right? Okay. So we'll be having 2 cube minus 2 cube is going to be 0. Then 2 minus 1 is going to be 1. Very good. So it is easy. Okay. Next is what? We have to calculate the derivative. Okay. So you can have this derivative, and hence you'll be having this is 3x square minus 4x plus 1. And again, we have to find the value of this derivative at 2. So what is the value of this derivative at 2?
5.
Is that 12 minus 8 and plus 1. So this is going to be 5. Okay. So that's what. Correct. Now, again, we find the next derivative. So what is going to be 6x minus. So what do you have? What is the double derivative we get here?
8.
Is that correct? I hope all of you are calculating with me. Okay. So what is the third derivative?
6.
6. Yes. What is the value of the third derivative at x equal to 2?
6.
It's going to be same, right? Okay. So now, okay. So somebody has asked me about the finite one. So what will happen to the next derivative?
It will be 0.
0. Yes. So that means, okay, though we have the formula, but all the remaining terms will be 0. Okay. So in the finite case, all the remaining terms will be 0. So we'll have this much expansion only. Okay. And hence we got all the terms. We are not able to find more terms. So we have to stop finding the derivative and write what is the expansion. Okay. So let us see. So we have to write the formula first. So what I can say is by Taylor series expansion. This is a standard abbreviation, so you can use it. Okay. So there is no more other meaning of TSE. So it is always Taylor series expansion. Okay. We have. So what we have here, it is going to be f of x is equal to f at a plus x minus a f dash at a plus x minus a bracket square by 2 factorial f double dash at a plus x minus a bracket cube by 3 factorial and f triple dash at a and so on. Okay. So now we know what is the value of a here. It's going to be 2. Okay. So we can write here. Here a is equal to 2. So we get, we are able to get is f of x is equal to f of a we have calculated is going to be 1. So this is x minus a and this is going to be 5 plus this is x minus a. The value of a we can put. So we want to find in terms of this a. So 2 x minus 2 bracket square by 2 factorial and then what is this value we have obtained is going to be 8. Okay, right. So is 8 here and then plus we'll be having x minus 2 bracket cube by 3 factorial and this is 6. The remaining all terms are going to be 0. So here we don't have to write that terms. Yeah, so here we don't need to write those terms and hence we can write here f of x is equal to. So we got 1 plus 5 times x minus 2 plus this 2 factorial is going to be 2 and so you can write here 4 times x minus 2 bracket square. And this 3 factorial is going to be 6. So we can write directly, this is x minus 2 bracket. So we got here the Taylor series expansion of the given function about x is equal to 2 is 1 plus 5 times x minus 2 plus 4 times x minus 2 bracket square plus x minus 2 bracket cube. Okay, so we can know. Now the question is whether we have obtained the correct expansion or not. Okay, so because we are done with our expansion, we got in terms of x minus 2. So here we have the term x minus 2, here we have the term x minus 2, and again we have the term x minus 2. So that was our question, and then we got the answer. But whether this answer is correct or not. Okay, so there is a easy check. Okay.
Yes.
What is the easy
We have
check? How you are able to check this easily? I'll give you the hint. Okay. Put x is equal to 0. Okay. So if you put x is equal to 0, your answer should be minus 1. And from this minus 1, where did this minus 1 come? So here it is a constant. So when you put x is equal to 0 in this expansion or in this function, you will get minus 1. So whatever the constant value that you should get when you put x is equal to 0. So let us try here. Put the value of x is equal to 0. So what we get? 1 plus 5 times minus 2 plus 4 times minus 2 square, and this is going to be minus 2 cube. So you can have 1 minus 10. This is plus, what is the sum you'll be having? This is going to be 16. And what this sum is going to be? Minus 8. Okay, so you can see what this value is going to be. Is that minus 1?
Yes, sir.
Yes, sir.
Okay. So that way you can check always that whether you have got the correct answer or not. Okay. So just put x is equal to 0 in Taylor series, whatever you obtain, and then you should get the value of the constant in the given expression. Okay. So if you can get the constant term, that means your answer is correct. Okay. And if you are not able to get the correct constant term after putting x is equal to 0 in the expansion, that means you need to check your calculation. Okay. So this is how it is easy to check. Okay. So you got this idea how to check?
Yes, sir.
Okay, that's good. Okay. So that's how we can have. Okay. Is there any?
Sir,
Yes.
could you scroll up for a second?
Yeah. Yes. Yes. Sure. Yes.
Sir, I simplified the answer, so I got the same equation. X cube minus 2x
Yes,
square plus
that's what the function will
Yes.
not change. Okay. We are representing the function in a different way.
Yes. Okay.
Okay. The function will not change. We are representing the function in a different way. So here, if I find the expansion about x is equal to 2, and if I find expansion about x is equal to 3, okay, after simplification, you will get the same function because you are representing f of x is equal to, okay, what you are representing, f of x is equal to, okay, so this f of x will be there always.
Okay.
So you will not get the different function, only the representation is different.
Yes.
So actually, this expansion is used in many cases. Okay, so that's why we are studying it. It is used in many cases. So to upgrade or to calibrate the instruments. Okay, so whatever the number of terms you will take, that will give you more better calibration. Okay, and what this particular point is, it is the point where you control or you have the control. Okay, so that is the point there you are tuning. So actually these expansions are used for tuning the machines, fine tuning. Okay, so this is the part when we try to design Okay, so then we use it rigorously. But right now, for mathematicians, it is just the expression. But for engineers, it is the tool. Okay, so that will help you to design or to tune the system. Okay, so is there any doubt?
No,
sir.
sir.
Okay, everything is okay. You got this example.
Yes, sir.
So that's great. You got this example.